Hi and welcome to this Leaving Cert Applied Maths video where we're going to look at impacts and collisions, and specifically we're going to look at the type 2 direct collisions. We're going to explore impacts and collisions for the new Applied Maths course, which is first tested in June 2023. There are 3 types of impacts and collisions that we can meet, and each of these has their own individual videos. So we have type 1s, which are impacts or single body collisions, type 2, which this video is about, direct collisions, and type 3, oblique collisions. The links to the videos for the other types are given in the description below.
So just a little bit of background about direct collisions before we get into some examples. These questions involve two particles colliding directly. What that means is they will either be one stopped and one is moving, or they will both be travelling along the same path. So although we are worried about the signs for velocity, we don't have to think about resolving it. We're going to use the Newton's law of restitution and the principle of conservation of momentum. Both of these are on page 51. So we're going to use Newton's experimental law. I'll call that Newton's law of restitution and the conservation of momentum. So you could also be asked about energy. So the two energy formulas that we could possibly need are potential energy mgh, kinetic energy a half mv squared, and these are both on page 55. So what I find is a little table like this is really useful for any time we are dealing with collisions where there is more than one particle. So just quickly to talk about vector versus scalar quantities. We have a section here coming from our log tables, and we have momentum. We're talking about Newton's experimental law, so that is using vector quantities. The conservation of momentum, again, using vector quantities. An impulse is a vector quantity. So that is, you can just use the I or the J component, whichever has changed. Energy is different. We're going to need the scalar here. So for example, kinetic energy requires speed. So that V stands for speed. What I find helpful to do is to actually put a little vector arrow on top of anything that is a vector. So like the I for impulse, I'll put it in like this. And it's a good way to kind of remind yourself what is vector and what's scalar. So the questions we're going to look at today, it's the 2010 question 5 part A, 2014 question 5 part A, 2012 question 5 part A, and 2016 question 5 part A. In general, what we see in the question 5s is we have part A, which is a direct collision, and then part B, which is an oblique collision. That's not always 100%, but it's a good rule of thumb for what we've seen in recent years. Okay, so let's take a look at the 2012 question 5 part A. I'm going to set up my little table and I'm going to do a little bit of a sketch so I can see what's going on. So A has mass m, B has mass 3m. So A is moving towards B with the speed of u, and B is stopped. So that gives me m 3m, u 0, and then the 2 I want to work out I'm going to call x and y. So first thing is Newton's law of restitution. So V1 minus V2 is equal to minus E times U1 minus U2. So that gives me x minus y is equal to minus EU. So that's clear. Equals minus EU. And that's equation 1. The second thing we're going to do, principle of conservation of momentum. And that is m times u plus 3m times 0, m times x plus 3m times y. Now there's a y in all terms, so we can divide across by y, and we get, changing it, x plus 3y is equal to u, and that's equation 2. So now we're going to do simultaneous equations. And we have equation 1 and equation 2. So 1 is x minus y is equal to minus EU. The second equation is x plus 3y equals u. I'm going to change the signs up above, so minus, plus, plus, and the x's eliminate. So 4y equals EU plus U. So y is equal to, I'm going to pull that u out in front, e plus 1 all over 4. I'm going to sub it back in. I'm going to take equation 2 because that hasn't got an e. And I have x plus 3 times u e plus 1 over 4. That equals u. So x is u minus 3 over 4 u e plus 1. If you prefer, you could write that all over 4, whatever way makes it easier for you. So if you prefer, you could write that as 3 over 4. We're going to try and combine these. So I'm going to multiply that by 4 and put it over 4. So we end up with 4u. I'm going to multiply this out. Minus 3ue minus 3u all over 4. I'm beginning to see very quickly my 4's and u's look quite similar, so just be so careful with your own and following my work. So x ends up being, I have u minus 3ue all over 4, and I would like to clean that up as u1 minus 3e over 4. So that gives us our two speeds. So there's y and there's x. So for part 2, if E is equal to 1/4, find the percentage loss in kinetic energy due to the collision. So we have our table up here, and I've subbed in what we've worked out in the previous part. However, I can work that out even further now because they told me that E was equal to 1/4. So knowing that E equals 1/4, I can do that substitution. So that's U bracket 1 minus 3 over 4 all over 4. And that works out as U over 16. And we can do the same for V2. And that's U bracket 1/4 plus 1 over 4, and that gives us 5U over 16. So we're going to talk about kinetic energy. So we need to understand the kinetic energy before and the kinetic energy after. So before, it's going to be a half mv squared. So that's mu squared over 2. Then after, kinetic energy after, and that's going to be a half m. Now my new v is u over 16 squared plus there's a second particle because the first time before that second particle wasn't moving. Mass is 3m and it's 5u over 16 squared. So we're going to need to work this out, and this works out as u squared over 512 plus, oh, wrong color, 75 u squared all over 512. We can clean that up by adding the two together and we get 76 over 512, but that simplifies it down to 19 u squared all over 128. And the question had asked us, just to remind us what the question was, the percentage loss in kinetic energy. So now we need to understand the loss. So the loss, it was mu squared over 2, and now it's 19 mu squared over 128. You can ignore that mu squared and simply put a half minus 19 over 128 into your calculator, and that will give us 45 mu squared all over 128. So therefore the percentage loss, we're going to put the loss, which is this, and we're going to put it over, because it's fractional, I'm going to divide it by the original amount. So mu squared over 2. So anytime we want to divide by a fraction, we instead multiply by the reciprocal. So that looks like 45 mu squared over 128 multiplied by 2 over mu squared. The mu squared cancel, so we will be able to get a number straight off. And then you can multiply that out. We get 90 over 128, and when we convert that into an actual percentage, that's going to give us the answer, which is 70.3%. So 2014 question 5 part A. A smooth sphere A of mass 2m moving with speed u collides directly with smooth sphere B of mass 7m that's at rest. So they've given us the diagram, so I'm going to fill in my information. I find it a lot easier to process when I can see the information like this. B then collides with a vertical wall which is perpendicular to the direction of motion of the spheres, and the coefficient of restitution is 1 over 2 for all collisions. Part I, show that the spheres will not collide for a second time, and what is the total loss of kinetic energy due to the impacts. So think about what's going to happen. A will hit B, and it will definitely send B heading towards the wall. We've been told that B collides at the wall, and when B hits the wall, it's going to come back. So if B is moving when it returns, the only way that they won't collide a second time is if A is moving in the opposite direction, i.e. to the left, and it's doing so faster than what B rebounds. So let's take a look at how we can approach this question. So I'm going to draw out my table for A and for B. I'm going to need a second one because B is going to hit the wall. And when we talk about B hitting the wall, we're going to have what is effectively like a single body collision. But let's start with A and B for now. So we have 2m, we have 7m, we have 0. Oh no, other way around. We have u and we have 0. And we have what I like to say x and y. So first thing we're going to do is Newton's law of restitution, which is v1 minus v2 is equal to minus e bracket u1 minus u2. So that is x minus y is equal to minus, we know e is a half, and we have u minus 0. So that is 2x minus 2y is equal to minus u. And that is equation 1. Second thing is the principal conservation momentum. m1u1 plus m2u2 is equal to m1v1 plus m2v2. So we have, back to my original color, so 2m times u plus 7m times 0 is equal to 2m times x plus 7m times y. The m's cancel out, so we're left with 2x plus 7y is equal to 2u, and that is equation 2. And we need to understand, well, what is that value of x and y in terms of u. So we'll take 1 and 2. 2x minus 2y is equal to minus u. 2x plus 7y is equal to 2u. I'm going to change the signs. I'll change the signs to the top one, it doesn't matter. Plus and plus. The x's eliminate. And we have 9y is equal to 3u. So y equals u over 3. I'm going to go back, it doesn't matter which one, I'm going to go to equation 1. And we have 2x minus 2u over 3 is equal to minus u. 2x is equal to minus u plus 2u over 3. So you can either, two options, do this on your calculator. So just ignore the u's. So you have a minus u, so that's just minus 1 plus 2/3. Or you can do highest or lowest common denominator, which will put that as minus 3u over 3. Either way, you'll end up with minus u over 3. So then x, final line, is equal to minus u over 6. So let's put that in. So minus u over 6, and that is u over 3. So basically what we've discovered is x is going to, particle A is going to go backwards. So that x is negative. So it's going to go left. So now we need to understand what will happen when B hits the wall. Okay, so let's talk about B hits the wall. So now we're back to single body collision. So what we have is E is equal to minus nu over the old velocity. So we need to understand. So we will see a rebounding, so it will change direction. That much we know for sure. The E is still a half is equal to, I don't know what the new velocity is. I'm going to use Z because I've already used X and Y. It was u over 3. So bringing that over, so we get minus 2z is equal to u over 3. So z is equal to minus u over 6. So that is the fact that B, after hitting the wall, is moving now to the left. The reason they're not going to collide, since z is equal to x, B will never catch up on A. Because they're travelling at the same speed. Therefore, there will be no further collisions. So let's take a look at the 2012 question 5 part A. 3 smooth spheres A, B and C of mass 3m, 2n, m and m lie at rest on a smooth horizontal table with their centres in a straight line. Sphere A is projected towards sphere B with speed 5 meters per second, and sphere A collides directly with B and then B collides directly with C. The coefficient of restitution between the spheres is E. Show that if E is greater than 3 minus root 5 over 2, there will be no further collisions. So we're going to look at the first collision, which is A and B. And they've told us here in the question that A is 3m and B is 2m. And sphere A is given, it's projected at 5 meters per second. So B is at rest. So before we have 5 meters per second, 0 meters per second, we have 3m and we have 2m. And we're going to try work on our after. So our x and our y. So let's work with need to solve restitution first. So v1 minus v2 is equal to minus e u1 minus u2. Now I'm not going to sub in a value for e because this is an inequality question. So I'm going to leave it in terms of e and then see if we can work to figure out what value or what range of values we can allow e to be. So we have x minus y is equal to minus e 5 minus 0. That gives us x minus y is equal to minus 5e, and that is equation 1. We then take a look at the principal of conservation and momentum, and that is 3m times 5 plus 2m times 0 is equal to 3m times x plus 2m times y. The m's here, because they're in each term, will cancel out, and we get 15 is equal to 3x plus 2y. I'm going to flip that around. 2y plus 3x is equal to 15, and that becomes equation 2. So working with equation 1 and equation 2, we're going to do simultaneous equations to work out x and y. Minus 5e, 2y plus, I'm actually going to flip this, and I'm going to write it as 3x plus 2y equals 15. So what I'm going to do is I'm going to multiply the top line by 2, and that will allow us to eliminate the y's. So we have 2x minus 2y is equal to minus 10e, and the second equation stays as is. The y's eliminate, and we're left with 5x equals 15 minus 10e. Going to divide across by 5, and that gives us 3 minus 2e. And then we go back to whichever of our equations we want. I'm actually going to go back to 2 because 1 has it in terms of e, so 2 will be a little bit easier to work with. So 3 times 3 minus 2e plus 2y equals 15. So that's 9 minus 6e plus 2y equals 15. 2y equals 6 plus 6e, so y is equal to 3 plus 3e. So we can fill that into the table. 3 minus 2e, 3 plus 3e. And now we need to look at the second collision. So now we're going to look at the second collision, which is between B and C, and we're going to set up a new table. So just let's look at a little diagram of what this looks like. So we have 2m and we have m. B has now been projected because of its last collision with 3 plus 3e. So we have 3 plus 3e and C is at rest. They are 2m and m respectively, and then I'm going to use a and b here because I've already used x and y. So first thing I'm going to do, Newton's law of restitution, and that's a minus b is equal to minus e, 3 plus 3e minus 0. And that can be cleaned up as a minus b is equal to minus 3e minus 3e squared. And that is equation 1. We then have principal conservation momentum. So we're going to have 2m by 3 plus 3e plus m times 0, and that should be equal to 2m, I probably have enough space here, 2m by a plus m times b. I'm going to need to do a little bit of a cleanup here. So we have, before I do a cleanup, I'm going to cancel out all these m's. Make it easier, 6 plus 6e is equal to 2a plus b. So 2a plus b is equal to 6 plus 6e. and that is equation 2. So now we'll do simultaneous equations. It is a little bit messy because of the algebra, but just focus on the a and the b. Minus 3e minus 3e squared, 2a plus b is equal to 6 plus 6e. We don't have to do anything because the b's will straight away eliminate. So we have 3a is equal to 6 plus 3e minus 3e squared. We can divide across by 3. So a is equal to 2 plus e minus e squared. So then whichever one we want, I'm going to take equation 2. Be a little bit easier. And we have 2 times 2 plus e minus e squared plus b is equal to 6 plus 6e. So 4 plus 2e minus 2e squared plus b is equal to 6 plus 6e. Rearranging that, b is equal to 6 minus 4, which is 2. 6e minus 2e plus 4e plus 2e squared. So they are our two after speeds. So now we need to think about what we can do to work out that e is greater than 3 minus root 5 over 2. So setting it up, we have 3 spheres, they're all moving in the same direction. And the reason we know they're all moving in the same direction is because we have our velocities lined up here. And remember that e cannot be bigger than 1. So if you take a look at them, if e can't be bigger than 1, then they will all be positive. So then in order for there to be no further collisions, we can say that VA, the velocity of A, would have to be less than the velocity of B, so it doesn't catch up, and that would in turn have to be less than the velocity of C. What that looks like for us is 3 minus 2e must be less than 2 plus e minus e squared, and in turn must be less than 2 plus 4e plus 2e squared. We only have to work with one part of it, so I'm going to work with this part because there's a nice left hand side there in 3 minus 2e. Otherwise I have 2 quadratics, but it doesn't really matter. So here we have 3 minus 2e minus 2 minus e plus e squared is less than 0. That is e squared minus 3e plus 1 is less than 0. So you should have hopefully covered quadratic inequalities in maths. So first thing is to make it into an equation. We can only solve the equation and use those answers to help us. Actually, factorization here won't work. So instead, we're going to have to go to minus b. So when we go to minus b, we're going to get e is equal to 3 minus root 5 over 2. And e is equal to 3 plus root 5 over 2. And then whatever way you want to work to get it, you can sketch it or you can do substitutions. We end up with 3 minus root 5 over 2 is less than e is less than 3 plus root 5 over 2. And that is where we get the part that they wanted us to have. And that will also come out if we look at this piece here. So we have e is greater than 3 minus root 5 over 2. And that is as we were asked. So we're going to look at the 2016 question 5 part A. And 2 small smooth spheres A of mass 2 kg and B of mass 3 kg are suspended by light strings from the ceiling as shown in the diagram. The distance from the ceiling to the centre of each sphere is 2 meters. Sphere A is drawn back 60 degrees and released from rest. A collides with B and rebounds. B swings through an angle of theta. The coefficient of restitution between the spheres is 3 over 4. Show that A strikes B with the speed of square root 2g meters per second and then find the speed of each sphere after the collision, and then find the value of theta. This is a really nice little question. So we're going to start with A. So we need to understand at what speed that A strikes B. So there's some information that they've told us. They've told us that this is 2 kg. They've told us that this is 60 degrees. And what we want to understand is the potential energy at this point. Because if we talk about the potential energy at that point, it should equal the kinetic energy at its lowest point. So we'll have mgh is going to be a half mv squared. So the mass doesn't really matter. And effectively we're going to need to know h, the height above the ground. So how high is this sphere above, not even the ground, its lowest point, because that is going to be where we're going to try and understand our potential energy, that height. So I'm going to make a little triangle here, and in this triangle we know that this is 2 meters. So we can work out this side here because we know that the angle is 60 degrees, and this is 2 cos 60 degrees, and that will allow us to understand a number that can help us calculate the height above the ground. So that gives us an answer of 1 meter. So if that height is 1 meter and its total of 2 meters, then it must be 1 meter above the ground. So this is g times 1 is equal to a half mv squared. I want to find v, so v squared is equal to 2g. Oh, sorry, that m has gone, so we just had a half v squared. And then v is going to be the square root of 2g, which is what they asked. So that's our part I. So then it wants the speed of each sphere after the collision. So now that we have a collision, we're going to be talking about a direct collision, and we're going to set up our table. So we now know particle A was traveling with the square root of 2g meters per second. Particle B is at rest. A is 2 kg, B is 3 kg, and we want to know our after. So I'm going to call that X and Y. So we're going to use Newton's law of restitution, and that is V1, so that's X minus Y is equal to minus 3/4 root 2g minus 0. So that gives us 4x minus 4y is equal to minus 3 root 2g, and that is equation 1. Then we're going to look at the principal conservation of momentum. So we have m, which is 2 times root 2g plus 3 times 0 is equal to 2x plus 3y. So cleaning that up, we get 2x plus 3y is equal to 2 square root of 2g, and that becomes equation 2. So simultaneous equations, we have 4x minus 4y is equal to minus 3 root 2g. I'm going to multiply number 2 by minus 2, so I get minus 4x minus 6y minus 4 root 2g. That allows my x's to eliminate. I get minus 10y is equal to minus 7 root 2g. So y is equal to 7 root 2g all over 10. I'm going to take equation 1, and that's 4x minus 4 times 7 root 2g all over 10 is equal to minus 3 root 2g. That's 4x equals minus 3 root 2g plus 14 root 2g over 5. Cleaning that up, I can put that in. So we've 3, 14 minus 15, and that works out as minus root 2g all over 20. Now we can write these just as decimals so we have a bit more sense of what's going on. So 0.22 meters per second. They did say speed, so anytime they say something like that, I will be saying put it into decimal. Just to be safe, you have both of your answers there. So that's the answer to part 2. So let's start with part 3 then. Find the value of theta. So I'm going to just take our swing here that we've been given in the diagram, and I'm going to put in our little right angle triangle. Now we're going to use the same logic we had before that we use with A, and this time we're going to say that the kinetic energy that we have as B starts moving should then match the potential energy just as it stops. So that means we have a half mv squared, and I have the speed above, should be equal to mgh. I'm going to put it in terms of g, and I'm going to get rid of our m's. So that is a half times 7 root 2g all over 10, and that's squared, and that's going to be equal to gh. So when we do that, we get 49 times 2g all over 200 is equal to gh. Our g's cancel, so our h is equal to 49 over 100, or easier, 0.49 meters. So that's how high it has come off the ground. So we are now talking about a height here of 0.49. Remember, the string was 2 meters, so this is still 2 meters. But this side here is now going to be 2 minus 0.49, so that's 1.51. And now we're going to be able to work with, we have hypotenuse and we have adjacent, so we can work with cos. So we have the cos of theta is 1.51 divided by 2, and we can work out theta as the cos inverse of that, 1.51 over 2. Make sure your calculator is in degrees, and that works out as 40.9 3.97 degrees. So depending on maybe different ways where you approach that, if you subbed in the 3.10, it might come out slightly different. Because we use the G's, it's a little bit more accurate, but anywhere in around 40.9, something that will round it up to about 41.